Welcome to this video series entitled Innovations in Diagnostic and Pharmaceutical Technology, focused on research materials and their applications, brought to you by Pentapharm. In this video, we'll review the origin of Prionex and how it's related to collagen and gelatin, essentially as a form of hydrolyzed collagen peptides. We'll also discuss the properties of this product and what is unique about the manufacturing process, as well as the physical attributes and properties of Prionex, including safety, solubility, and the amino acid composition. We'll also use case studies to discuss applications of Prionex. Finally, we're excited to share some details about a new form factor of Prionex that will be available soon. Prionex is a hydrolyzed collagen peptide. To discuss how Prionex is derived, it's important to start with collagen. Collagen is the most abundant protein in mammals, and it is found throughout the body, mostly in connective tissues such as skin, cartilage, bone, tendons, and ligaments. It's important because it contributes to the strength of these structures. Gelatin is derived from the irreversible partial hydrolysis of collagen, and this can be achieved through acid treatment, which results in a type A product, or alkaline treatment with a high pH, which delivers a type B product. Hydrolyzed collagen peptides are created through the enzymatic digestion of gelatin. Where gelatin is gel-forming, hydrolyzed collagen peptides are non-gelling. Different preparation methods of hydrolyzed collagen peptides will yield products that vary greatly in their physical and functional attributes. They may have a different gelling property, something called bloom. Other qualities related to the size of different fragments may vary, including the variety of polypeptide fragments, the size, the molecular weight, and the net charge. Some processes may produce product that varies from lot to lot, and some may introduce contaminants from the manufacturing process. The specific parameters used to extract, solubilize, heat denature, enzymatically digest, and whether acid or alkaline treatment is used will greatly affect the degree of hydrolysis and functional properties of the resulting product. Technically, there are numerous ways to produce gelatin and hydrolyzed collagen peptides that will yield end products that will all function differently. So what is unique about Prionex? It's a unique proprietary preparation derived from porcine skin, or pig skin, that is type A or acid treated to produce the hydrolyzed collagen peptides. It's available as a 10% aqueous solution with absolutely nothing added to it. There are no additive stabilizers or preservatives, and it is free of cartilage, bone, or plasma fragments, or any contaminants from the manufacturing process. This process is extremely consistent and highly controlled, producing excellent lot-to-lot consistency, which ensures that distribution and functional properties are preserved. Prionex will yield a higher molecular weight material than standard processes to produce hydrolyzed collagen peptides, which makes it a useful alternative to bovine serum albumin, or BSA. The average molecular weight of Prionex is 20 kilodaltons, and it ranges from 5 to 45 kilodaltons. Other processes that produce hydrolyzed collagen peptides tend to yield much smaller fragments ranging in size from 3 to 6 kilodaltons. Considering that BSA has a molecular weight of about 66 kilodaltons, Prionex with a larger molecular weight than other products may be a more suitable replacement for BSA. Whenever BSA attributes are required, a product that is similar in size could act as a reasonable alternative. This diagram illustrates how Prionex is developed. It starts with the porcine skin that has been ground and defatted, then enzymatically digested with pepsin. The insoluble material is removed through filtration, and the collagen is purified. Then it undergoes acid treatment, making it a type A gelatin product. It's then heated to 145 degrees Celsius while it's adjusted to 10% solids. It then goes through an aseptic 0.2 micron filtration, yielding the final product, Prionex, which is a 10% sterile and additive-free solution. Here is some of the key analytical data behind Prionex. It has a clear yellowish appearance with a pH between 6 and 7.5. The dry residue, or percent solids, is between 9 and 11%, with an average of 10% mass per volume. As mentioned earlier, the molecular weight is an average of 20 kilodaltons with a range of 5 to 45 kilodaltons. The sodium chloride content is between 0.55 and 0.7%. Total nitrogen is between 1.5 and 1.9% mass per volume, and the concentration of heavy metals is less than 20 parts per million. Endotoxin testing via the limulus amoebocyte lysate, or LAL method, shows less than 10 endotoxin units per milliliter, so the product is considered non-pyrogenic. The polypeptide content is between 8.2 and 10.5%, and Prionex is sterile. So why is this material called Prionex? It's free of prion disease agents that are always a risk in bovine-sourced materials. Since it is derived from porcine sources, it does not carry a risk of bovine spongiform encephalopathy, or BSE, otherwise known as mad cow disease. The treatment at 145 degrees Celsius will inactivate any pathogen including bacteria, viruses, and other prion-like infectious agents. This heat treatment also inactivates any contaminant enzymatic activity that would be undesirable. Prionex is extremely safe. In guinea pigs, it's been shown to be non-antigenic and non-allergenic. In the mouse model, there is no toxicity noted after oral ingestion of Prionex of up to 1,250 grams per kilogram body weight, and no toxicity after injection of up to 25 milliliters per kilogram body weight. For both oral and intravenous administration, Prionex has not been shown to cause harm. Prionex is highly soluble in water, diluted electrolyte solutions, glycerol, in dimethyl sulfoxide, or DMSO, in ethanol solutions of less than 75%, and in ammonium sulfate solutions of less than 20%. The amino acid composition makes Prionex unique. It's comparable to collagen because it is collagen-derived. Collagen has repeats of glycine XY amino acids, where X and Y are frequently proline and hydroxyproline amino acid residues, and this is clearly reflected in the amino acid composition of Prionex. It has a relatively low aromatic amino acid content, including phenylalanine, tryptophan, and tyrosine, which means that there is minimal absorbance at 280 nanometers in the UV spectrum as compared to bovine serum albumin, or BSA. In this graph, you'll note that there is a large peak in the blue line, representing BSA at 280 nanometers. The purple line represents Prionex, and you can see the contrast as there is very low absorbance shown by the absence of a large peak in the purple line. This makes Prionex useful for applications or assays that require 280 nanometer wavelengths to be used. Prionex is a proven stabilizer for in vitro diagnostic applications. These can include protein stabilization, preservation of biological activity, adsorption prevention, shelf life extension, lyophilization, and as a heat treatment excipient, and as a blocking agent in immunoassays to reduce nonspecific binding. This is an example of how Prionex can help stabilize protein solutions. In this case, a cardiac marker control, which contains troponin IC, a large multimeric protein, and BNP32, a short hormone 32 amino acid polypeptide, was evaluated after 6 days of stress at 25 degrees Celsius. There were 3 different preparations. One was made in a 5% HSA, or human serum albumin solution, one was a 5% Prionex solution, and the third was an equal blend of the two. This graph shows that Prionex effectively preserved the biological activity of both proteins. Prionex increased the storage stability, it increased the temperature stability, and it preserved the biological activity of these two compounds. Here's another example of how Prionex can stabilize proteins. In this case, the clotting time of thrombin preparations were evaluated after 0, 10, and 30 days at 37 degrees Celsius. 1% Prionex was evaluated against 1% BSA and a blank, which did not contain any stabilizer. The results of the graph show that Prionex significantly improved the stabilization of thrombin after 30 days of accelerated stability testing. Again, it increased storage stability, increased temperature stability, and preserved the biological activity of thrombin. Another application of Prionex is for the prevention of adsorption loss. The adsorption of trypsin in a suspension of glass particles was evaluated after 2 and 5 minutes of agitation at room temperature. Once again, a 1% Prionex solution was evaluated against 1% BSA and a blank that did not contain any additional stabilizer. The graph to the right shows an extreme loss of biological activity due to adsorption of trypsin with the stabilizer-free preparation, while this loss was lower with and comparable between BSA and Prionex. In this case, Prionex could be used as a direct replacement for BSA, as it results in similar, if not equal, prevention of adsorption loss against glass particles. Prionex prevented adsorption into glass surfaces and preserved biological activity. Prionex is also useful in immunoassay blocking. Here, a lateral flow for the detection of SARS-CoV-2 spike antigen, which is COVID-19, was evaluated in a running buffer that contained phosphate-buffered saline and twine and was made with and without 0.5% Prionex. These were tested with contrived positive samples by spiking 1 microgram per milliliter of recombinant spike antigen into each sample. The photo to the right shows that the running buffer without Prionex gave a strong positive result with the 1 microgram per milliliter contrived sample, but you see a false positive there with the negative sample. Adding 0.5% Prionex into the running buffer was able to clean up this assay. You see a little bit of a diminished signal with the 1 microgram per milliliter, but you see 0 nonspecific binding there at the test line with the Prionex. The result is a strong false positive signal in the negative control and the preparation made without Prionex. This illustrates that Prionex can effectively reduce nonspecific binding when used as a blocking agent in immunoassays. Let's review how Prionex works as a protein stabilizer. Although BSA is a form of albumin and it's quite often used as a protein stabilizer, it may be incompatible with some protein preparations due to having several ligand binding pockets. Albumin is a carrier molecule in the body, and these ligand binding pockets are how it carries substances throughout the body. The complex structure of BSA is also prone to heat stress-induced conformational changes that can lead to binding, aggregation, and unfolding of the tertiary structure. Prionex, however, is composed of HCP or hydrolyzed collagen peptides, which have been shown to be structurally inert. They lack major secondary or tertiary structures that can fold into unwanted binding pockets. The highly charged nature of the amino acid content may also explain stabilization and the immunoassay blocking through various electrostatic interactions. Lastly, the thermal processing of Prionex renders the material free from any proteolytic contaminant enzymatic activity. Watch for a new product coming to market, Prionex, in a lyophilized pellet format. This format consists of freeze-dried pellets as opposed to the 10% solution, which can offer added convenience. It will enable you to prepare a more concentrated Prionex solution than the 10% solution may allow. It will also present a convenient option when sample dilution is a concern. The addition of the freeze-dried pellets will not add significant volume compared to the 10% solution. Another advantage of this new format is reduced open bottle contamination risk. Thank you for watching this presentation summarizing key features and uses of Prionex.